Okay, thanks for the introduction. Well, I would also first thank the organizers for inviting me. And I'm sorry I cannot join you in person, but I'm very excited to join you virtually to share with you our recent work. And this is a joint work with Zhengyu Huang from Cron, Sebastian from PostStem, and Andrew from Caltech. And our work is also on archive with the same title. Yeah, and feel free to interrupt me during this talk. Yeah. And our work is motivated by accelerating climate science. These days, we have more and more data which can be collected by the satellites or generated from these high fidelity local simulations. We try to use this data to calibrate the global climate model. Here, this global climate model, you can think it as a coupling of several PDE systems. You have the atmosphere, land, and ocean. And such model is very expensive. And most of the time, you can only use it as a black box because it's really very difficult to compute the derivative, especially you have this coupling between different systems. And so this motivates us to consider efficient derivative Bayesian calibration approaches. And so I believe most of you are very familiar with this inverse problem formula. Here we try to find some unknown parameter theta from noisy observation y, which are related by the forward operator g here, which maps the unknown parameter theta to the observation y. And this forward operator g is the evaluation of it can be very expensive, and it might involve solving the complicated PDE system. And we assume we have some observation error eta. That's a Gaussian distribution with error covariance sigma eta. Besides getting the best theta, we also want to know the uncertainty. So we can formulate it in this Bayesian framework. Here, we try to sample or approximate the posterior distribution theta, conditional on y. And based on Bayesian's rule, this posterior consists of two parts, the likelihood parts and the prior parts. The likelihood part is proportional to e to the power minus phi, and phi represents the data misfits, which is the difference between the observation and the model prediction, which is normalized by the error covariance matrix sigma eta. And if we further assume that the prior distribution is a Gaussian, the whole posterior distribution is proportional to e to the power minus phi r, and phi r consists of the data misfit term and also the prior term, and it's a quadratic function here. And so our goal is to sample such distribution with an unknown normalization factor. I think there are two main avenues for such sampling problems. So the first category is based on invariant measures and ergodicity ideas. Here for this idea, you first construct some transitional kernel phi I, of psi I, and here the posterior distribution is the invariant distribution of this kernel. And based on ergodicity, starting from any distribution, and keeping applying this transitional kernel on it, it will finally converge to the posterior distribution. And there are many methods belongs to this category. For example, Markov chain Monte Carlo methods and long-join dynamics. Here, the transition kernel psi I is the Markov kernel. And recently, there are many interacting particle approaches. where different transitional kernel nodes have been constructed. Another category of methods are based on the coupling idea. Here you have this coupling kernel psi c, which helps to move the prior to the posterior in certain time. And there are many methods belong to this category. For example, the sequential Monte Carlo method, where the transitional kernel is based on important sampling, and the ensemble or unscented Kalman filtering, where the transitional kernel is based on Gaussian approximation. And recently, there are transport map methods where you build different transport map to mimic the effects of the transitional kernel. Yeah, these are, so now we have these two ideas. And I believe the methods in the first category generally require like 10,000 model runs or even more, like Markov to Monte Carlo methods. Imagine for the complicated simulation, like the climate simulation, each simulation run takes several hours or several days. So we cannot afford 10,000 model runs. And in this talk, we will focus on coupling approach, where we try to move the prior to the posterior in a very efficient way. So now I will first give you an example that's based on coupling idea. So that's the Kalman methodology. Here, assume we have the prior, that's a Gaussian. Here, prior of theta, that's a Gaussian distribution. Then we construct the joint distribution of theta and g theta plus eta. And we project it onto the nearest Gaussian. So that means we only approximate the first two moments. So here the expectation of theta is R0 because we know it. And the expectation of g theta plus eta, we define it as x hat. And the covariance of theta, we know it, it's sigma 0 here. And the covariance between theta and g theta plus eta, we define it as c hat c theta x. And the covariance of g theta plus eta, we define it as c hat xx. After we have this joint Gaussian distribution, we can easily compute the conditional distribution of theta, conditional on that g theta plus eta equals y here. Because the conditional distribution of a Gaussian is still a Gaussian, and we have an analytical formula, so we can get a Gaussian approximation of the posterior distribution. So for this algorithm, the main challenge is how to compute these red terms. Imagine if g is a linear function, we can compute them analytically, right? And if g is nonlinear, we need to use different nonlinear Kalman filters. So here we need to use different nonlinear Kalman filters to approximate the expectation and or covariance of g theta. And we know theta is a Gaussian distribution here. That's our assumption. The most popular Kalman filter is this extended Kalman filter. That's based on the linearization idea. Here you linearize g theta at the mean of theta R0 here, and you keep the first two terms. So the approximation is a linear function. So with this approximation, you can compute the expectation or covariance in analytical formula. However, this method requires computing the derivative of dg here. Another popular Kalman filter is Ensemble Kalman filter, which relies on Monte Carlo method. So you first sample a bunch of particles, theta I, from the Gaussian distribution, and then you compute the expectation or covariance empirically here. Yeah. Another Kalman filter is called unscented Kalman filter. Here you can think the expectation or covariance as the integration with a Gaussian density function. And then because they are integrations, you can design very specific Gaussian quadrature rule. So the expectation or the integration can be approximated as a summation of the products of the quadrature weights and the function evaluation at these quadrature points. And you choose this weight or quadrature points. Here, the quadrature points locations depend on the mean and the covariance. And if you choose these parameters carefully, you can get certain order of accuracy for the approximation. And there are also many different Gaussian quadrature rules. So these are the basic idea of different Kalman filters. Now I will show you some numerical demonstration here. So imagine if theta is a Gaussian distribution here, and g theta represents some nonlinear functions. You have square root here and exponential here. And now if you want to estimate the distribution of g theta, you can use different Kalman filters. And here in these figures, I show you the reference solution that's obtained by Monte Carlo methods, where the distribution is represented by these gray dots. And in the first figure, I show you the approximation obtained by extended Kalman filter. And because you compute the derivative, so you only need to evaluate the function once. So the cost is 1. And for the ensemble Kalman filter, here I show you the result with 50 ensemble particles. So you need to evaluate the function 50 times. For the unscented Kalman filter, here I use a quadrature rule with 5 quadrature points. So you need to evaluate the function 5 times. And you can see the ensemble Kalman filter's result is very similar to the extended Kalman filter result, also represents the distribution very well. And in general, ensemble Kalman filter can approximate this distribution exactly if you take j to infinity. But the unscented Kalman filter is more efficient for a Gaussian approximation. And with this different Kalman filter, you can approximate these red terms, and this gives you the Kalman filtering method to approximate the posterior distribution. Here, that's a Kalman filtering method. You move the prior to the posterior in one step. And if you introduce artificial time t here, you can think like the prior is actually prior times e to the power minus 0, phi here. So, and the posterior is the distribution at time 1 here, because it's rho prior times e to the minus 1 phi here. So you can think like Kalman filtering idea moves the prior to the posterior in 1 unit time. And you can think we can, instead of moving it in one step, we can move it in maybe n step. Then, for example, we can divide this 1 unit time into some small time step with delta t. That will give you the iterative Kalman filtering idea. So here you first scale the error covariance matrix by delta t. Then the likelihood function or the data misfit phi is scaled by delta t here as well. And then you approximate it by the Kalman filtering idea. In previous slides, you can, and you keep doing it. that gives you the iterative Kalman filtering methods. So you can start from the prior, and each time you move it a little bit with delta t here. And you can think after n time steps, you can get some approximation of the posterior distribution. So that's a coupling idea. You always introduce a time, and you move it, and you move the prior to the posterior in 1 unit time. However, for most methods based on coupling ideas, this temporal error can be accumulated. For example, if at each time step you have maybe delta t error, then at the end, after n time steps, you will have order 1 error. The approximation might not be satisfactory. So this motivates us to think about how to fix it. And so this is our solution. We try to combine the coupling idea and the invariant measures and the ergodicity idea here. So because if you have invariant measure, and you can keep iteration, and this will not introduce temporal error. So we first construct this fixed point iteration. Here, for each iteration, you move the density function rho n to the posterior, to something proportional to the posterior, to the power gamma over gamma plus 1 times rho n to the power 1 over gamma plus 1. So here you can see the posterior density function is actually the fixed point of this iteration. So here we use the invariant measure idea. And so by keep iterating this, any initial density function will converge to the posterior density function. And to get this fixed point iteration, we introduce 2 transitional kernels here. And the first transitional kernel psi prediction, psi p here, that moves rho n to rho hat n plus 1. That's proportional to rho n to the power 1 over gamma plus 1. So this first kernel, you can think it just push the density function, and so it acts like exploration here. And also this first kernel does not depend on the observation or the forward operator G. Then we construct a second transitional kernel psi analysis, psi A here, that further moves this rho hat n plus 1 to rho n plus 1. That's proportional to the posterior to the power gamma over gamma plus 1 times rho hat n plus 1. And you can see by composition, these 2 kernels, you get the update equation from rho n to posterior to the power gamma plus over gamma plus 1 times rho n to the power 1 over gamma plus 1. That's the fixed point iteration we want. And if you write this in the integration form, you can see we have applied first kernel and then second kernel, and the posterior density function is the invariant density for the combination of these 2 kernels. Yeah, and so far is it clear? Okay, although I cannot hear anything. And to implement this idea, we introduce our mean field dynamic system that consists of 2 steps. We have the prediction step and analysis step, which correspond to these 2 kernels. So for the prediction step, we add noise to the dynamic system, here omega n plus 1. And the noise we assume is a Gaussian. Here the covariance matrix is gamma times Cn. Here Cn is the covariance estimation of theta n, because the prediction step depends on the law of the theta n, so we call it a mean field dynamic system here. And now assume the distribution of theta n, the density function of theta n is rho n. That's a Gaussian here. And because the summation of two Gaussian is still a Gaussian, so the density function of theta n plus 1 is also a Gaussian. Here, the mean will be the same. The covariance matrix becomes 1 plus gamma times Cn. Because Gaussian belongs to exponential family, so we know this rho hat n plus 1 is proportional to rho n to the power 1 over gamma plus 1. That's what we want for the prediction kernel. And the second step is the analysis step. We introduce this augmented observation equation. Here, this forward operator or augmented forward operator has two parts. We have our forward operator G here, and we also put theta here. And for the observation, we have, for the augmented observation, we have our observation Y here. And we also put our prior mean R0 here. For the noise, we assume it's still a Gaussian. And we have our error covariance matrix here. We also put our prior covariance matrix here. And we scale it by gamma plus 1 over gamma. Assume now we have the distribution of theta n plus 1. That's the rho hat. And we assume it's a Gaussian here we obtained from the previous step. And now we can use Kalman method to approximate the conditional distribution of theta n plus 1 conditional on xn plus 1. That's the Kalman filtering idea, the coupling idea I introduced you at the beginning. This conditional distribution has a prior term and the likelihood term. And this prior term is rho hat n plus 1. And if you compute the likelihood term, it's actually the posterior to the power gamma over gamma plus 1. Because we augment the system, so we have the real prior information R0, sigma 0 here. And this power is actually the scaling factor here, gamma over plus 1 over gamma. And we can use any Kalman filters or any coupling approach to approximate this term. And then we can get different algorithms. So here we can also describe our algorithm in another way. Here we introduce the mean field dynamic system. And that's also the hidden Markov model. Yeah. And we have our evolution equation, this one. And we have our observation equation here. That's our augmented system. After you have this dynamic system, you can apply any filters on it. Like that will be the same as the method that's used in data simulation community. And you can, so let's first denote the capital Yn as the observation sets collected from time 1 to time n. Then any filter can give you an approximation of theta n conditional on Yn. We call it rho n. And also after the evolution, you get the distribution of theta n plus 1 conditional on capital Yn. That's rho hat n plus 1. And you keep applying the filter, you will get an updated equation for the density function rho n. And this will be the fixed point iteration I introduced you before. So is this clear now? Okay. So, and actually we can do some linear analysis by assuming that the operator G is linear and the gamma is greater than 0. If we have that the prior covariance and the initial covariance matrices are symmetric positive definite, the iteration for the conditional mean and the covariance matrix characterize the distribution of theta n conditional on capital Yn converge exponentially fast to the posterior mean and the covariance matrix. So we have the convergence in the linear case. And our algorithm also has this affine invariant property. So here we may write our algorithm in this update equation. As this updated equation here, we update the mean and covariance from last time step to the next time step, and consider any invertible affine mapping that maps x to x star. Here we assume A is invertible, and further define these vectors by A times this vector plus B, and we also define G theta as G A inverse theta minus B, and also these are the corresponding transformation of the matrices. Our algorithm actually is invariant with respect to this invertible affine mapping. So we have the relation between M stars Mn star C star. That's the same. So this has a desirable consequence that performance of our method is independent of the aspect ratio in highly anisotropic objective functions. So imagine you have some planar shape density, posterior density, and it will be after the affine map, you can make it make it very Gaussian, like a circle. So our method will be very robust if you have an isotropic objective function. So now I will show you some numerical studies. Here we compare 3 categories of methods. The first category has our Kalman inversion methods. So we apply different Kalman filters on our mean field dynamical system. So we can get unscented Kalman inversion, ensemble Kalman inversion, and the ensemble adjustment or transform Kalman inversion. So here the ensemble adjustment or transform Kalman filters are variants of ensemble Kalman filters, which treat the stochastic term in ensemble Kalman filter deterministically. And another category has recent proposed Gaussian approximation algorithms. They include ensemble Kalman sampler that's based on depth Langevin dynamics and consensus-based sampler. You will hear more about it tomorrow, I think. And the last category is iterative Kalman filtering. Here, that's an iterative Kalman filtering I introduced you at the beginning. So you cut the unit time into small time delta t, and you keep applying Kalman filter on it. So we have iterative unscented Kalman filtering, iterative ensemble Kalman filtering, and iterative ensemble adjustment or transform Kalman filtering. So here at the beginning, I will show you the results for some linear problems. Here we have analytical solution for the posterior distribution. We consider this linear system where theta is a 2x1 unknown vector. And we consider overdetermined system where our our forward operator G is a 3x2 matrix. So we have 3 observations, and also underdetermined system. Here, the matrix G is a 1x2 matrix. So we only have 1 observation. So these are the results. This slide is quite dense, so I will explain it carefully. So this is the results for the overdetermined linear problem. Here we have in the first row, we have the mean errors obtained by different methods. And in the second row, we have the relative covariance error that's obtained by different methods. So here in the first panel, I show you the results obtained by Kalman inversion methods with our mean field dynamic system. These are n with capital I here. And you can see most of them can converge exponentially fast. The only exception is this orange curve. That's the ensemble Kalman inversion, because ensemble Kalman filter introduces noise in each step to maintain the consistency of the covariance estimation. So you have this random noise in it, and this random noise will go to 0 if you have infinite many particles. But in reality, for this case, we only use 10 particles. So you have this error here. And this purple curve and brown curve, these are the results obtained by ensemble Kalman sampler and consensus-based sampler. Because both of them introduce noise in each iteration, so they cannot converge, but you have some noise oscillations. And so in this panel, I show you the results obtained by different iterative Kalman filtering methods. You can see most of them can get exactly 0 at time 1, because iterative Kalman filtering can be exact for linear problem. The only exception is this orange curve, that's iterative ensemble Kalman filter, because it introduces noise, as I just mentioned. And here, this purple curve is obtained by iterative ensemble adjustment Kalman filter. But for this simulation, at the beginning, the empirical mean or covariance does not match the prior mean or prior covariance exactly. So the error introduced at the beginning will be carried on. And so it cannot converge. And that's also highlights the issue of all the coupling methods, like the error introduced during the simulation will be carried on. And for the relative error, relative covariance error, the results are the same. The story is the same. Like you can see, if you introduce noise, you cannot get converged results. And for coupling methods, the error introduced at the beginning or during the simulation will be carried on. So, and for underdetermined linear system, the story is the same. We can still get exponential convergence for our Kalman inversion methods. Now I will show you a 2-parameter model problem. That's a nonlinear problem. We try to recover 2 unknown parameters, one in the coefficients and one at the boundary for this one-dimensional elliptic boundary value problem. Our observations are the solution Px at different points. So for example, for the well-determined system, we have observations that's at 0.05 and 0.75. And for the underdetermined system, we only have one observation here. So for this case, we do not have analytic solution for the posterior distribution. So we use Markov chain Monte Carlo method to estimate it. So here, the figure is organized the same as the previous example. We have relative mean error for the first row and relative covariance error for the second row. And you can see all our Kalman inversion methods can converge very fast at the beginning, and then they flatten out because Gaussian approximation has some error for nonlinear problems. And you can see ensemble Kalman inversion and ensemble Kalman sampler or consensus-based samplers, they have oscillations due to the random noise. And for this case, iterative Kalman filtering cannot get exactly solution, and the errors are much larger. So for the underdetermined system, the story is the same, and the iterative Kalman filters have even larger error here. And specifically, this red curve obtained by ensemble transform Kalman inversion diverges a little bit. So we think ensemble transform Kalman filter is less robust for this case compared with unscented Kalman filter or ensemble adjustment Kalman filter. So finally, I will show you a high dimensional inverse problem. Here, that's the classical Darcy flow problem. We try to estimate the permeability field A from the point evaluation of the pressure field P here. Here, that's the solution. The reference pressure field, we have these 49 equidistant point-wise measurements. And here we assume our prior distribution of the permeability field is a log Gaussian here. And it can be expanded on the Kahuna-Larver basis. And now we try to find the first 128 modes, 128 coefficients theta k here from these 49 point-wise measurements. So here, this figure, I show you the estimated KL expansion parameters, coefficients theta I. Here, the middle curve, I show you the mean estimation for these different coefficients. And on top and bottom, I show you the associated 3 sigma confidence intervals. So here, all these curves are overlapped, almost overlap. For example, we have the precondition Craig-Nicholson MCMC, that's the orange curve. It requires like 10 to the power 6 iterations. And we also have results obtained by different Kalman inversion methods, like the unscented or ensemble adjustment Kalman inversion. They can converge in fewer than 10 iterations. That highlights the efficiency of our method. And we can get almost the same result as MCMC for the first 2 moments estimations. So that's a conclusion and the future work. So here in this talk, we try to introduce you an idea to solve inverse problem by first pairing the forward operator with a stochastic dynamic system. Here you can design any stochastic dynamic system. You have the evolution equation and observation equation, and then you can apply different Kalman filtering, different filtering techniques on it. If you design it carefully, skip this one. For example, we design some very special mean field dynamic system, which combines coupling and invariant measures and ergodicity ideas. And then we apply Kalman filters on it to perform Bayesian inference in a very efficient way. And in the future, we will also consider multimodal distribution and a model for error. So here, this is our paper, and also in the GitHub repository, we have more applications. We also use our method to calibrate a 3D climate model in fewer than 10 iterations. Thank you for your time.